Can you hear me?
Hello, yes, we can.
Okay, thank you very much. Okay, I switch to the pulpit. Okay, last time we were talking about operation amplifiers. I hope everyone understood what's going on with this circuit. We are talking about basic mathematical properties of the when we are using operation amplifiers. Yeah, summing, we could divide, we could measure the difference of the voltages and so on. But we can also make some more complex mathematical operation. And as you know, probably the filtering is also a mathematical concept. Yes, it's we can use some mathematical equations to filter a signal, filter the signal, for example, the sinusoidal signal. So we can also use the amplifiers to build some filters. As you remember from our, I don't know, first or second lecture, we use some capacitors and resistors to build simple filters. So we could use low pass or high pass filters using just two elements, resistors and capacitor. And we start with the similar situation. So we've got a typical RC filter with cutoff frequency of 1 divided by 2p RC. Yes, this is typical cutoff frequency. If you remember, it is the 3 decibel drop of this input signal. Yes, when the input signal drops 3 decibels, this is the frequency of the cutoff of the filter. So we can build a typical filter, but we use a buffer, non-inverting amplifier, yes, just to fill the signal and to make sure that the other system out of this filter will not will have not current going through this filter. Yes, because this situation, if you remember, that the buffer causes that we've got infinitive input and zero output resistance. So, in the matter of fact, what happened here is no fact on the input. Yeah. So this is a solution. Of course, this is the easiest, and this is the easiest. This is the easiest example. Of course, you remember the cutoff frequency. This is the equation. So this is just two parameters, just C and R. So this is not complicated to calculate the cutoff frequency. Yes, this is the chart of this filter. So we've got the cutoff frequency. This is the 3 decibel, and usually this is the typical 20 decibel per decade for the RC filters. So this is the typical situation of the filter made of resistor, capacitor, and buffer. Okay, so but this is usable, but if we have the property of the amplifier of high impedance and low impedance of input and low impedance of output, we can make more complicated situation. Okay, this first example, it was in the matter of fact first stage. Yes, because first stage, it means 20 decibel per decade, but we can design some more complicated situation. And this is 2 stages. Of course, we can use 1 stage filter and then another 1 stage filter, and we will have the second stage filter, but it's easier to use just 1 amplifier. So in the matter of fact, we can find out that we can we can design a filter, a second order filter. This is an example of the low pass filter. So if you can see, we've got some feedback here and the feedback here, because in the matter of fact, this is the amplifier, yes, with the gauge of R2 to R1, it's +1. This is a typical gauge of the non-inverting amplifier. Yeah. And the cutoff frequency, it is the equation for cutoff frequency. So we've got the connection of these 2 resistors and these 2 capacitors. So in the matter of fact, we can build any filter we want, but I will tell about this later. Okay. Similarly, we can build a high pass filter. Yes, this is the filter that filters lower frequencies, and similarly the cutoff frequency is the same as the CR filter for the basic components. So we can produce a filter of the properties that we do not pass the low frequencies. But the problem is that the operation amplifier do not have the infinitive response in all the frequencies. Yes, because of course it's built of real elements. So it do not have infinitive frequency response. So this is a typical characteristic of the amplifier. So we can see that it's work good up to, let's say, 1 kilohertz. Okay, so for the frequencies higher than this, we can drop off voltage gain. So we do not have. Of course, this is, let's say, typical amplifiers, because as you remember, we got a lot of types of amplifier, and we do have amplifiers where this frequency is very, very high, megahertz or terahertz, of course, but typical amplifier that we use for measurements are like this. So the frequency is about 1 or 10 kilohertz, and then the voltage gain drops. Okay, so in this situation, we in the matter of fact, we did produce, when we use this high pass filter, so it passes higher frequencies, but in the matter of fact, we will have the situation of this. Yes, so this is the high pass frequencies, high pass filter, yeah, but in generally this is low pass filter because the properties of the amplifier. So do remember that if you design an amplifier, especially high pass, so the frequencies will drop, the gain will drop for higher frequencies because the amplifier is not infinitive. Yes, so it's not ideal. Okay, so in generally, in this situation, the gain, the voltage gain, of course, it is output to input signal, and this is this is taken from this chart. This is the voltage gain for the frequency, and this is the frequency we wanted and the cutoff frequency. So we can calculate voltage gain for the special frequencies. Okay. Of course, as I told you, this is the first order, first stage filter. It is 20 decibels, and if we want to have filters that have higher response to the frequency, we add some another stages. Yes, we add some another orders. I will show you how it works later. Okay, so that was the example, simple example of the high pass filter and low pass filter. Of course, we can design some active filter, because when we're using operation amplifier, we say we design some active filters, but we can design some band pass filter. Okay, so if we use in series high pass filter and low pass filter, we will first make the filtration of the high pass and then the low pass. Okay, so we will have the situation, but generally you can see that we've got the high pass filter here and low pass here. But of course, this is the example of the design. So in generally, we have stop band. Yes, this is the frequency up to the stop frequency, cutoff frequency of the high pass filter, and we've got this is the stop band of the high pass, and this is the stop band on the low pass. And this is in this situation, we've got the frequencies from this point to this point. This is called pass band frequency. So this is the frequencies that the signal will pass the filters without any distortion, without any changes. Okay, so this is the bandwidth of the filter. So we've got the band pass filter and we've got the bandwidth of this filter. We can calculate this. This is another situation when we can design a filter. Here we've got two filters in series, yes, and this situation is one in one circuit. So generally the gain is connected with the relation of these two resistors, and the cutoff frequency of low pass and high pass filters is connected with this capacitance. So we can calculate the cutoff frequencies and band pass of the filter. Of course, this is the same situation. So we can calculate these elements. Yes, this is another. This was the inverting pass. This is the infinitive gain feedback. So we've got the different designs of filters. And in this case, we can say that we've got we can design filters with different orders. Yes, starting from the first order. So it was the 20 decibels per decade, and further second, third, and so on. As you can see, this is the ideal, of course. This calls a brick wall response, but we are not able to achieve such a situation. So this is the ideal cutoff frequencies, because if we set cutoff frequency, in this case 1 Hertz, we would like not to have signals on this side and have none of the signal here. But in a matter of fact, using real filters, we can find out that changing the order, we are going towards the ideal filter. Yes, but it causes another problems. Okay, this is the general equation when we change the order of the filter. Okay, so we can calculate the gain of the filter. Okay. Fortunately, for more complicated filters, we do not have to calculate the parameters by ourselves. We've got some tools. Okay. Of course, there are many examples of such a tools. So this is a tools. In the matter of fact, I do utilize, but you can use tools with other fields. This is a program, tools for Filter Pro. This is designed by Texas Instruments, so you can use it online. In the matter of fact, because it's not a program; it's an internet tool. Can you see the filter, the tool?
Yes, we can.
Okay, so in the matter of fact, we start with, we have to choose what kind of filter we would like to design. Let's say we are going to design low pass filter. Okay, this should be the easiest one. Okay, so in this case, we can design a filter with different parameters, and we can choose. This is the gain, so generally in then decibels, 0 decibels, so it means that we've got 1 volt per 1 volt, so we have no gain. Okay, this is the cutoff frequency. Let's say it's 100 hertz, and this is the ripple. So if we change the ripple, so you can see that we change the response time. Okay, let's stop with the 1. It is the easiest. Of course, we can, that was the standard parameters, but we can change the order of the filter. The easiest one, okay, start with the order with 1, so with 20 decibels per decade, and you can see that the magnitude response for the frequency is like this. Okay, so this is the 500 hertz will be like here, so it should be 3 decibels drop of the signal will be here. Okay. In this program, we can also design filters designed by different scientists. No, we can't. Okay, I switched out to the auto, and then I can choose what kind of filter I do expect. Yes, because this is the example of Basel filter, but we can choose also Butterford or Chebyshev. This is, you probably heard about this man. They are the mathematics who discovered the properties of the filtering by mathematical equation. So using a different coefficient of the filter, we can achieve different properties. So you can see that we can have different properties of the filter. This is the Chebyshev. You can see it's the magnitude is sharply going down, and Chebyshev and the Basel going slower. Okay, but of course there are different properties in the phase. You can see this is the Basel, this is the Butterford, and Chebyshev. Okay, so because in filters we do change both the magnitude and the phase of the signal, so we have to choose what is more important, or the phase or the signals. If you can see, the Butterford. The Butterford will change the Butterford changes the phase lower. So we use the Butterford, okay, and then we can how to design the filter topology. Select, okay. Okay, and then we can see that we have the proposition of the design. Yes, this is a topology. This is probably it makes just one capacitor, one resistor. Awesome. Okay, and the program designed calculates the parameters, calculates what kind of resistors or what kind of capacitors we should use to achieve this frequency, 500 Hertz frequency. Okay, so we can, as you can see, we do not have to calculate everything, and we just use such a tool. Of course, we do not have such a resistor, so we can recalculate this. Okay, in this tool we can't recalculate, but there are tools that we can change the resistors and change one resistor, and then the program will recalculate the another elements. Okay, so this is a typical situation. Of course, we can change the stage probably. So let's say we will use the stage 6. Select. And we can see that we have to use 3 amplifiers, 3 operation amplifiers, and the parameters of the calculated by the program. So to achieve better better filtration, faster filtration, or the sharper filtration, we should use more elements. Yeah. So this is the response of the designed filter, and of course the phase. Of course, calculate the phase depends on the frequency. Okay. So using such a tools, we can calculate what we want. Of course, maybe it's better to use not so many elements, because we do not have to establish the properties of these elements, and the noises will be sums. So sometimes it's better to use filter with lower order than use a lot of elements, because each of the elements cause also the noises of the in the system. Okay. Okay, do you have any question about the filters? Okay, no. Okay, so we close the filter. Okay, so generally this is the end of the problem of the it's not the end of the generally the end of the amplifiers, operation amplifiers, but for this lecture is the end. So if someone wanted to know something more and can study more. Okay, so today I'm going to say we are going towards batteries, accumulators, and energy sources, because any of circuits, of course active circuit, which needs some supply, needs the supply. so it needs some energy sources. Of course, we've got energy in our plugs, so we've got the outside energy, but in general, we are going more towards some mobile elements, some mobile system. So we more and more wanted to go to the accumulators and to batteries, yes, because we want to be independent. So if we are going to build some mobile, some elements which we can put in our pocket, so we need the source of energy that are independent. So probably we'll use some batteries and the accumulators. Okay, what was the history of the battery, of the accumulators and the another power sources? We start. That was the first element that was found out. It was the galvanic cells. Yes, this is the beginning of the battery. So it was found that 2000 years ago, there was a jar. Yeah, there was a jar with some special materials that was used to electrically place a gold on the silver. Yes, so if we, because the gold was and is the best, the most wanted material, so probably someone wanted to make a fake, so they use a jar that could plate a gold on a silver, so the silver could pretend a gold. Yes, and it, as you found, it was 2000 years ago, and up to today we do not know how it worked, but it probably worked because they found some element that were silver and some gold element on it, and it was something like galvanic cells. Of course, there was Alessandro Volta was working about how to store the energy, how to have the source of energy. And he discovered that there are some elements. For example, if we join the zinc and silver disk, 1, 2, yes, on another. And if we separate them by the wet cloth containing a salt or weak acid, we will have some voltage drop, we will have some energy. Yes, so he discovered a first battery, first Western civilization battery. Okay, so as you can see, this is the similar situation as it was 2000 years ago. We use silver and some substances, in this case, zinc. Okay. Of course, the Volta was the first, but then the Michael Faraday in the 90s also work on how to store the energy in some substances or in some elements. And he discovered the fundamentals of the galvanic cells and electrically. And he could let's say, put electrochemistry on a film, and he discovered how it works, and it was the first scientific basis of how it could work. Okay, so it was the Michael Faraday. So he discovered that they developed a first practical lead acid storage cells. Yes. So they use some plumbum and the acid. We do still use them in our accumulators in cars. So it comes from the Faraday discovered. So it still have 200 years. So we do not change everything from this. Of course, it's not true, but because we discover something more, but it will be later. Okay, so how the galvanic cells worked and what kind of electrode we should use to achieve a different voltages, the different storage of the voltages in our battery or in our accumulator. I will show a short film.
In this video, we're going to talk about galvanic cells, which are also called...
Okay, this is a short film about galvanic cells, and the guy will explain how it works. Okay, can you see the film?
Yes, we can.
Okay, I started.
In this video, we're going to talk about galvanic cells, which are also called voltaic cells. So what are they? Well, galvanic or voltaic cells are devices that use a chemical reaction to create electricity. Specifically, the type of chemical reaction that they use is called an oxidation-reduction reaction. But we'll talk more about that later. Now, galvanic or voltaic cells may be totally new terms for you, but I'm willing to bet that you use these devices almost every single day of your life. And that's because a battery is an example of a galvanic or voltaic cell. There are chemicals inside batteries, and those chemicals react together in an oxidation-reduction reaction that makes electricity. And this is what powers your cell phone or your flashlight or whatever the battery is hooked up to. So let's learn more about these devices and see how a chemical reaction can create electricity. Okay, so I think for the rest of this video, I'm just going to call these voltaic cells instead of calling them galvanic or voltaic cells. All right? So I now want to talk about the parts of a basic voltaic cell, one that you could actually make in the lab. So here's what they are. First, we start with 2 beakers or containers of water. And into one of them, we dissolve some zinc sulfate to make a solution. And then into the other, we dissolve some copper sulfate and make a solution with that. So we got these 2 solutions. Then we take a piece of zinc metal, like this one right here, and put that in the zinc sulfate solution. And then over here, we take a piece of copper metal and we put that in the copper sulfate solution. The next thing we do is we take a wire, a metal wire, and we use that to connect the 2 pieces of metal together. And when we do this, something amazing starts happening. Electrons start moving through this wire. They move from the zinc metal into the copper metal. Now, this is a big deal because moving electrons are what make electricity. So when we hook this wire together with the pieces of metal and electrons start moving through it, we have electricity. We have electricity moving through this wire. And what we could actually do is we could take a little light bulb like this and hook it up to this wire, and the light bulb would turn on because there's electricity moving through this wire. Now, to be really specific, there's one more part of the voltaic cell, and that's a little tube called a salt bridge that connects these two solutions. We'll talk more about the salt bridge at the very end of this video, but right now I'm going to leave it out because I want to make sure that we keep things simple. So this is the basic setup of a voltaic cell. Now, I want to zoom in so that we can see the atoms and electrons in the metal and in the solution and understand what's causing electrons to move along this wire and create electricity. Here's our magnification of the different parts of the voltaic cell. We can see some of the atoms in the metals and in the solution. So let me show you what's what. This is a magnification of the area here. These zinc atoms are on the edge of the piece of the zinc metal. And then these Zn2+ ions are in the solution. They're part of this ZnSO4 solution. I'm not showing the SO4 here. I just want to focus in on the zinc. So zinc ions in the solution and these zinc atoms in the piece of zinc. Then over here, we have these Cu2+ ions that are in the CuSO4 solution. They're dissolved here. And then these copper atoms are on the edge of this piece of copper here. Okay? So we've got a wire that connects the zinc and the copper. And we've said that when we hook everything together, electrons start flowing through this wire. Well, why is that? Well, when we connect these two pieces of metal with wire, it kind of starts a tug of war between the zinc and the copper. They're having a tug of war for the electrons. One of them wins and one of them loses. It turns out that Cu2+, these atoms here, Cu2+ has a really strong pull for the electrons. But then on the other hand, zinc, these zinc atoms, zinc has a weaker pull for electrons. So in this tug of war, Cu2+ ends up winning. Let me show you how this happens. So Cu2+ really wants electrons. So it's kind of like it calls over here to zinc, which has a weaker pull on the electrons, and says, hey, zinc, give me some of your electrons. And zinc's kind of weak, so it's like, oh, okay. And what happens is, let's say this zinc atom here gives away 2 of its electrons. And these electrons enter the wire and move towards the copper. Now, when zinc gives away those 2 electrons, it causes its charge to change. It's lost 2 electrons, so it gets a positive charge, and it becomes Zn2+. Now, changing from neutral zinc to zinc 2+ has a big effect on this atom. And that's because neutral atoms make up solid metal, but metal ions usually dissolve in water. So after this zinc atom turns into Zn2+, because it lost these electrons, it's no longer part of the solid metal anymore. And it floats off, it dissolves into the solution. Okay, so that's what happens to the zinc. Then over here, these electrons make their way down the wire to the copper, and one of these Cu2+ ions, which really wants electrons, is going to come over here, and these 2 electrons are going to be added to the Cu2+ ion. Gaining these 2 electrons is going to get rid of that 2+ charge that was on the copper, and that is going to turn it into a neutral atom, which means that it is no longer going to be able to dissolve in solution, and it's going to become part of the solid copper metal here. Okay? So that's what happens to the copper. Now notice that for this whole process to happen, electrons have to move through this wire, and that's where the electricity, the electron movement comes from. Let's see that one more time. So zinc loses 2 of its electrons here. Those move through the wire. Loss of those 2 electrons causes zinc to take on a 2+ charge. It is then going to dissolve in the solution. These 2 electrons are going to move over here to copper. And one of these Cu2+ ions that really wants electrons is going to come, it's going to take them in, and that is going to get rid of the Cu2+. It's going to get rid of the 2+ charge, and this neutral copper atom is now going to become part of this solid piece of copper metal. So that is where this electron movement through the wire is coming from. Zinc loses these 2 electrons. They move through the wire, creating electricity. They come over here, and they join up with the Cu2+, turning it into neutral copper. We have these electrons moving through the wire here, creating electricity. So that is how we get electricity, from these electrons moving from the zinc over here into the copper. And if this happens long enough, we actually see these 2 pieces of metal change, right? Like these zinc atoms keep coming off of this piece of zinc. So it's essentially dissolving. And over time, what we'll see is that this piece of zinc actually starts to dissolve. It gets smaller and smaller. But then on the other hand, those Cu2+ ions are coming out of solution and are attaching to the solid copper. And so they're going to make this piece of solid copper bigger and bigger. And so if we let this voltaic cell run for long enough, we'll eventually see that these 2 pieces of metal actually change size and shape. Here's some diagrams for the process that's happening in the voltaic cell. I want to describe what's going on in terms of oxidation and reduction. So over here, one of these neutral zinc atoms is losing electrons. So that means that oxidation is happening on this side of the voltaic cell. And over here, this Cu2+ ion is gaining 2 electrons to turn into a neutral copper atom. So reduction or gain of electrons is happening over here. Now, we can give names to these 2 parts of the voltaic cell based on whether oxidation or reduction takes place. So the cathode is the name that we give for the site of reduction, where reduction happens. So reduction is happening here, which means that the piece of copper is the cathode, the site of reduction. And the piece of zinc over here is where oxidation is happening. The piece of zinc is going to be the anode. So reduction at the cathode on copper, oxidation at the anode on zinc. Now, let's write reactions for the 2 processes that are happening here, okay? First, let's write the reaction for reduction. We're starting with Cu2+, and this Cu2+ is dissolved in solution. So I'm going to write that with an AQ for aqueous after it to show that it's dissolved in solution. Now, this Cu2+ gains 2 electrons, so I'll write plus 2E-, and that gives us a neutral copper atom. So I just write Cu with no charge after it. That shows that it's neutral, and then it's part of a solid metal, so I write an S after it. So this is the reaction for the reduction process. Over here, the reaction for the oxidation process. We start out with a neutral zinc atom. And this neutral zinc atom is part of the solid piece of zinc. So I'm going to put this S here for solid. Now it loses 2 electrons. To show that we lose something in a chemical reaction, we put it on the other side of the arrow. Okay? So I'm not going to write anything right here. I'm going to put this arrow. I'll leave the electrons for last. Losing the electrons turns the neutral zinc atom into a Zn2+ ion. Zn2+ that is now dissolved in solution. So I'll write AQ here. And then finally, to show that I lost those 2 electrons here, I'll put plus 2e minus on this side. So this is the reaction for the oxidation. Now these 2 reactions that I wrote, we call them half reactions because each one of them tells half the story of the oxidation reduction process. And we can actually give names to these 2 parts of the voltaic cell as if each one of them is half of the big picture. We call this the oxidation half cell. It's half of the voltaic cell where the oxidation is taking place. And we call this the reduction half cell. It's half of the voltaic cell where reduction is taking place. And it is these half reactions that show what's going on in each one of the half shells. In each one of the half cells. I said half shells. It's like Teenage Mutant Ninja Turtles coming back to haunt me from the 80s. Anyway, we have these 2 half reactions, and we can put them together to get a net ionic equation, which shows the overall oxidation and reduction process. We start with solid neutral zinc and Cu2 plus ion, and then at the end of the process, we're left with zinc 2 plus ion, and then we have solid copper. This is a net ionic equation that we get from adding together these 2 half reactions. Now, when we're talking about voltaic cells, we're often asked to represent them in cell notation, which is a shorthand abbreviation of the chemical reactions in the voltaic cell. It's a way that we can show what's going on without drawing a picture of the whole thing, okay? Cell notation is sometimes referred to as a cell diagram, just so you know. So here's how we would write what's going on in this voltaic cell using cell notation. We start on the left with the oxidation process, okay? How does the oxidation process start? Well, I have the half reaction up here. It starts with solid zinc, okay? So I will write Zn solid right here. That's how the oxidation begins. Then I put this line here, and I show what we end up with in the oxidation process, which is Zn2+, okay? So Zn2+, and that is dissolved in water. It's part of the solution. It's aqueous. So this shows the oxidation process that happens in the half cell over here, okay? Then I put 2 lines like this, and these 2 lines represent the physical boundary between these 2 half cells, or you can think of them representing the salt bridge. Okay, now on the right, I put information about the reduction process. So the reduction process begins with Cu2 plus aqueous, Cu2 plus aqueous, and then I will put another one of these lines, and the reduction process ends with Cu solid. So there's Cu solid. So this is how we can sum up what's going on in this voltaic cell using cell notation. We have the oxidation process, and then 2 lines showing the boundary, and then we have the reduction process. So finally, we've talked a little bit about the salt bridge. I said we discuss it at the very end. So let me take a minute or 2 and explain what the salt bridge is, what it does, and why it's important in a voltaic cell. The salt bridge helps to balance out charge in the voltaic cell. Here's what I mean. The 2 solutions are made up of both positive ions and negative ions. I didn't show the negative ions before. Those are these yellow things. I just showed the zinc and the copper. But along with these metal ions are these polyatomic ions, sulfate, SO4 2-. It's a sulfur with 4 oxygens, and the whole thing has a 2- charge. I didn't want to have to keep using this thing, so I've just abbreviated these as SO4 2-. But the point is, the negative charge from the sulfate balances out the positive charge from the zinc or from the copper. So right here in my 2 half cells, the charges are balanced out. But let's look at what happens as the voltaic cell begins to run for a while. Okay? Over here, these zinc atoms are going to give electrons to copper. So they are going to end up with a charge. I'm not showing the electrons here, but electrons are getting sent up here as these turn into Zn2 plus ions and as they enter the solution. Now over here, as electrons come over, these Cu2 plus ions will turn into neutrally charged copper atoms and attach to the metal. Now look at what's happened to the charge here. Okay? Now we have all of these Zn2 pluses, but we have only a few of the SO42 minuses. So after just a little while, positive charge really begins to build up in this half cell. And then over here, as the positively charged ions like this lose their charge by gaining electrons and turn into neutrally charged copper, now there are a whole lot more SO42 minuses than there are Cu2 pluses. So a negative charge begins to build up on this side. And if this positive and negative charge build up too much, the cell can't run anymore. It can't continue to make electricity. So that is where the salt bridge comes in. Let me get rid of this wire and show you what the salt bridge looks like. Here is the salt bridge. It is a tube shaped like an upside down U that in our case is filled with sodium chloride. You can see the Na plus and the Cl minus ions. Now at the ends of the salt bridge there are cotton plugs, a little bit of cotton there. And the cotton prevents the solution from just pouring out into the half cells. But these ions are able to slowly pass through the cotton plugs, and here's what happens. We said that negative charge is going to start building up in the half cell over here. And so the positively charged Na plus, is going to begin moving over into this half cell to help balance out the charge. So the Na plus ions are going to begin moving in this direction to balance out the negative charge. And over here we said that positive charge begins to build up. The Cl minus ions are going to begin moving through the salt bridge to come out through the cotton and help to balance out the positive charge that builds up on this side of the voltaic cell. So over time, what we're going to see is we're going to see that the Cl minuses move in this direction to balance out the positive charge that builds up here. And then we'll see that the Na pluses begin to move to this side to balance out the negative charge that builds up here. A salt bridge helps to balance these charges to make sure that they don't build up too much, and that would prevent the voltaic cell from being able to work. Wow, so we just learned so much about galvanic or voltaic cells. Okay, so here's the basic structure of a voltaic cell. We have the zinc sulfate solution here, copper sulfate solution here. We have zinc metal and copper metal. Now, when we hook this all together, electrons start flowing from the zinc to the copper. And that's because copper that's in the solution has a strong pull for electrons, whereas the zinc has a weaker pull, so the copper wins. As electrons move from the zinc to the copper, they are lost in the zinc, so oxidation takes place, and they're gained here in the copper, so reduction takes place over here. We call this the oxidation half cell, and we call this the reduction half cell, because oxidation is happening over here, the piece of zinc is the anode, because reduction is happening over here, the piece of copper is the cathode. Then finally we can write half reactions for the two processes that are happening in the different half cells. Here is solid zinc losing 2 electrons because they're moving out to turn into a zinc 2 plus ion, which is going to enter the solution. And then over here, Cu2 plus ion that's in the solution gains 2 electrons and turns into solid copper It's going to attach to this metal right here. And then finally, we can sum all of this up by writing this cell diagram or cell notation, which shows everything that's happening in a shorthand abbreviated form. Zn solid, then a line, Zn2 plus aqueous. This shows the oxidation part. Then we have these two lines representing the salt bridge or the boundary between these two cells. And then we have the reduction part, Cu2 plus, line, giving us Cu solid. So that is how a device like a galvanic or voltaic cell uses a chemical reaction to create electricity.
Okay. So I hope you understood everything about the galvanic cells. Of course, this is just the example how the simplest galvanic cells works. So if you can see some chemical reaction, some movement of electrons, some movement of another part of solutions, cause that we have the ability to move the electrons, and in another hand, we have the ability to have the difference of the voltage. So we've got some kind of battery. Yes. In this example, it was shown that we could use a zinc and the cuprum as the anode and the cathode. So, but it is not we can use different materials, and this is the table where we can see what is the potential of the materials. This potential is connected with the guy was talking about how much he wants the electrons and how weak how the cuprum wants the electrons and how zinc is weak and he loses the electrons. So cuprum wants the electron in plus 34 volts, and zinc is weak and loses the electrons in the minus 76 volts. So this materials wants to lose electrons, and this material wants to connect the electrons. Yes, they want more electrons, and this part is weak and they lose the electrons. So changing the plate, changing the material of the anode and the cathode, we can change the difference of the voltage and change the difference of our battery properties. Okay, but what's the problem of the galvanic cell? The problem of galvanic cell, as the guy said, is that we loses the material of the zinc. Yes, and we add some material of the copper. But the process is not endless, yeah, because he loses the material, so the ions goes to the material. So in some situation, at the end, we will have no zinc anode, and the copper anode we will have no SiO4 elements in this solution, so the process will stop. So this is a good solution for to produce a battery. Yes, because the problem is also that can we reverse this process? Yes, so adding some voltages here and moving the electrons in the opposite way, are we able to put the ions of the zinc on the anode? No, we do not have the possibility. So this process is able only in the one way. So in this situation, we have just a battery, so we can't reverse the process. Okay, so using copper and zinc, we have a battery of 1.1 volt of energy. Yes, but is it good or not? it depends. Yes, this is the first. This is just the beginning of our history of galvanic cells and batteries. Okay, so it was found by Low Ari in the 90s. He discovered some alkaline cell batteries. So this is, for example, the most important was that it was a dry cell. So it is similar what we are using nowadays. So we use alkaline dry cells, dry batteries. Okay, so it was, as we can see, 70 years ago. It's not very far. And it was the first commercial battery, and he used not the solution of the acid, but the solution of KOH. Yes. So he used some corrosive substances, and in this situation we could have the possibility to have the battery with 5 to 9 times longer. So because we do not use such much material of the zinc and copper, so to use another materials, and in this situation we could have better batteries. Okay, but still we were not able to reverse this process, so it could be made in only once. So it's not the best solution because we have to throw these elements away. It is not very good solution. So the matter of fact, scientists were, yeah.
I have a question about previous slide.
This alkaline?
No, with voltages for elements.
This one?
Yes. So lithium is very common in batteries today, but I didn't heard about usage of fluorine. But it's on the top. But it's I don't think it's used anywhere.
This is just a theory. This is the theoretical properties of you do not hear probably about chloride elements, yeah, because it's not a metal in the matter of fact. But
okay.
we can imagine we can build something like this, okay? The chloride and the phosphor is not the phosphor is more metal than chloride, but from the chemical point of view, there are metals, yeah, but from mechanical point of view, they are not metal. So,
okay. Thank you.
Okay, so what was to discover? The problem was to store the energy not only for once, yes. So to build a construction that could store the energy, and we can recharge the battery, or then in this situation accumulate. Yes, so of course we can use the Plumbum solution. Yes, this is the first solution, as you heard from 200 years ago discovered. So we can recharge the process of Plumbum in our batteries, but the Plumbum is not the best substance to use at all, because it's very heavy and it's toxic and so on. So scientists wanted to discover, engineers wanted to discover some small elements that could store energy and they could be rechargeable. The first combination they could find that if we connect nickel and cadmium elements, we can have, and of course some acid in between them, we can reverse the process. So the ions of nickel and cadmium can be reversely put on the plates. Yes, and this is the chemical process, of course, that allows us to build a high efficiency element that could store the energy. Yes, of course, not only for high elements, but we can build some small devices, small elements, yes, small batteries. Of course, they can deliver high currents and store the energy in this charge and discharge process, yes. And this is the example how it works. So we've got the plate of cadmium, which is negative, and some plate of nickel. Yes, this is the plate of nickel. Of course, we've got some separation between them and acid inside. Okay, so in this solution, we've got something like accumulator, simple battery, which can reverse the process, and we can charge it. Okay, so this is the chemical reaction. So as we can see, we loses ion of the cadmium, and they are put on the nickel. So, but it can, as I said, we can reverse the process. Okay. Okay. So what are the properties of such an accumulator? Because we can say it's not a battery, it is accumulator because we can charge them. The voltage between nickel and cadmium plates are more or less 1.2 volts. 1.2 volts. This is the voltage on the battery because of the nickel cadmium accumulator. If you remember the typical alkaline voltage, the alkaline batteries have 1.5 volts of energy, yes, of voltage drop on it. So we can, this kind of accumulator, we can charge and discharge about 1,000 times. Yes, so we can put the energy on the accumulator and discharge with more or less high current efficiency. Yes, because in this kind of accumulator we can take from this accumulator very high current comparing another solution. Okay, and of course this accumulator works in the typical temperature ranges, has a good performance for low temperatures, so they do not lose the ability to store the energy for lower temperatures. As you remember, our plumbum batteries, plumbum accumulators lose the energy due to the temperature. So this nickel cadmium do not lose up to -20, -30 Celsius degree. There is no changes. The resistance is again in a high temperatures. Resistance is in proper electric use. Resistance, a shock and vibration. So this is very important because this solution, we use the solution how to design the batteries causes that it's shock and vibration resistance. So we can't easily break the accumulator. This do not require any another services, so we do not have to change the electrolyte in it, so it's closed and ready to use. And the installation is cheap, and generally it is a cheap accumulator, and we can store a density of power about 50 to 150 watts per hour per liter or per kilogram. Okay, never mind, per liter of, this is the liter of the accumulator. Yes. But they have some advantages, and the nickel cadmium has some disadvantages, of course, as everything. The nickel cadmium batteries, the nickel cadmium accumulators, has something called memory effect. Memory effect is caused, I don't know why it's caused, but it happened when we charge the accumulator, we charge to full, and we discharge to the half, for example, and we charge it again, and discharge to the half, and charge again to the full. We are going to lose the density of energy. I don't know why, but if we have to go back to the full of the ability to store the energy, we have to discharge this nickel cadmium accumulator to the nearest zero, and then charge it again. So this kind of accumulator is better to use in the full charge and discharge process. Yes, so it has this memory effect, and we have to remember about this. Okay, so it should be unloaded and discharged in fully cycles, because we will have this memory effect, and we will not able to store all of the energy we could store in the cells. Okay, this is the this is the chart how nickel cadmium accumulator behaves due to the time when with the current of 1C, because 1C means one capacity. So if we got the capacity of the accumulator by 550 milliamperes, yeah, this is the capacity. So if we are using a current 150 milliamperes, yeah, so we have this. We will have this line. Yeah. So we start. I don't know why. Maybe it's 5 or 4 cells together connected, because we've got the voltage of 6.8. But we should start from 1.4. Yes, 1.4. While 1.5 is the typical voltage on fully charged accumulator, and then we will use the voltage, but we will have the current going through the cells. Yes, but if we use higher current, we will use it faster. Of course, we do know that the current connects to the resistivity of the element, so we can see that the nickel cadmium accumulators has the resistivity not very low. Okay, so we lose some properties of the battery, some properties of the accumulator on the accumulator, so it's going to hit probably. Okay.
Excuse me.
Yeah.
Can we somehow reverse this memory effect or if it occurs, then the battery is damaged?
Yes. I told you, because if we are using full cycle, yes, full charge and discharge cycle, we do not have this memory effect. But if the memory effect happens, we have to discharge this accumulator to the zero. Yeah, so we fully discharge this accumulator and fully charge, and it should be better. But generally, it's not 100% of the capacity of the accumulator. So it's better to use these processes fully charge and fully discharge. But if we didn't do this, so then we will have this memory effect. We can discharge the battery, fully discharge and fully charge, and it should be better. Okay?
Okay, thank you.
I also have a question.
Yeah?
if you would want watt-hour rating of our battery, we want area below the curve from previous slide.
Yeah, this one.
Yeah. So watt-hour is area under the right or no?
Sorry, I can't hear you very well. So
Watt-hour is area below this curve.
this is time, minutes, hour. I don't know.
Yes.
This is the current. This is the voltage time curve. Yes. So if we sum this, of course, so this is the capacity of the. Yes, this is the capacity of the accumulator. Yes. This area. Yes. That was the question or not?
In watt hours?
In 1 hour.
Watt.
Is the,
Watt. Watt.
I don't know what's the problem. one you know in the power in watts? No.
Yes, watts, not one.
Yes, value. Okay, this is 1C. Yes, it means that we have the current of 550 milliamperes. Yeah, and this we can sum it in the time of 150 minutes. Yes, so this is the power. Yeah.
Okay, thank you.
Okay, so we are talking about the discharge. Yes, this is the discharge process of the nickel-cadmium accumulator. And how can we charge the batteries? Generally, nickel-cadmium accumulators are very well chargeable. So we can do this in many ways. We have no ability to say that it's something we can do to charge this battery. Generally, we shouldn't exceed the voltage on the battery. So generally, we can make a voltage source set on the 1.5 volt, and the battery will charge. But in our processes, we wanted to charge it faster. Yes, because generally you are in a hurry, so we would like to charge in faster. So generally, it was found that the nickel-cadmium batteries at the end of process of charging, they have something like maximum point of voltage. So this is of course the charge time. Yes, this is in time. Yeah, we change the voltage. So we start off 0.1 or something like that when we discharge, and the voltage will be higher. Yes, up to 1.55 or something like this. And then if we still charge it, the voltage will drop. So if we discover some elements, some devices that will find out the moment when it's going lower, in this we can stop the charging process. Okay, so this could be faster because in this case we could use higher current to recharge the accumulator, and we are feeling, well, we want to find the maximum of the voltage, and if we achieve this voltage, we wait a moment and end the process of the charging. Okay, that's okay for you? Okay, this is just a charging process of this element. Okay, the next type of accumulator, or battery, or we can say maybe it's not a battery but accumulator. It's a battery made of metal and nickel. This is the hybrid of nickel and metal batteries. We can say it is an NAMH batteries or NEMH batteries. It is commonly used nowadays because we can store more energy in it. So in the matter of fact, we've got negative and positive electrodes made of nickel and metal, some kind of metal, and we can store an energy in the process. Yes, this is the chemical process for storing the energy. Okay, what are the properties of the nickel metal hydride cells? The voltage is a bit higher because 1.2 volts, so maybe it's similar to the nickel one. We can charge it similarly, charge of course and discharge, we can similarly 100 times, 1000 times. They have fast self-discharge time and shorter service life, so in general I do not have a service because it's on the one piece. And we can store higher energy because you remember in the nickel it was 50 to 150. Here we've got 140 to 300 watts per watt-hours per liter of the battery. Yes. Okay, this lazy battery, never mind. What are advantages and disadvantages of such a battery? This is the discharge process. Yes, this is the example for such a battery that have the capacity 1900 milliamperes. So you can see that using different discharge currents, we achieve different voltages on the cell. So you can see that the voltages are dropping faster. So generally, metal, this metal nickel batteries or nickel accumulators are used for devices which do not use much more current. Yes, because the resistivity of the elements is higher, so we can't use high currents on it. So it's better for devices which uses more current, it's better to use nickel accumulators, and for devices which do not need such much current, we can use, and we need more capacity of the elements, so we can use this metal nickel batteries. Okay. How can we reverse this process of discharge? Okay, we can also, similarly to the nickel batteries, we can charge the nickel, this kind of batteries, and this is the charge process, and it's similar to the cadmium nickel batteries. So in this case also we are all settings the voltage to 0.5, for example, and we say it's after 1 hour is full, or we are sensing the maximum of the voltage on the cell, because it still have the effect that in 100% of the capacity he loses the voltage he drops the voltage on the cells. Okay, so we can't discharge, and so we can't overcharge the element because he loses the voltage. Okay, so we sense the maximum and we stop the process of charging. Okay. Okay. The disadvantage of such an accumulator is that the amount of energy, the amount of stored energy in it depends on the number of cycles. In nickel cadmium batteries, we had the problem of memory effect. In this kind of batteries, we do not have this problem, but we loses the ability to store the energy due to the number of cycles. And this process is also cost and depends on the current we use to discharge these batteries. As you can see, if we use the battery, which typically is discharged by 1C, so current, yes. So the capacity, it's after 500 times discharge and charge, it's drop a bit, okay? But if we use higher currents, like for example C3C, we loses the ability to store the energy. Here you can see that after 400 times we have no possibility to store the energy. So the nickel metal accumulators batteries are better to use for smaller currents, because we can store the energy more times, more charges and charging and discharging processes, and use the nickel cadmium batteries for higher currents, because they are better for higher currents. Okay, so what next? Okay, but nowadays we are going more towards another kind of accumulator, another kind of batteries. It is lithium-ion batteries. I hope you heard about it many times. So it was proposed by Exxon in the late 70s, and this accumulator was developed by lithium cobalt oxide in 79, but they had some safety problem. So because they are very explosive. So they replaced the cobalt oxide with ions, with lithium ions. So generally, they finished their work in the 1990s, and it is the Sony that commercialized the ions batteries, the lithium ion batteries, and they had still the problems. And nowadays we have also the problem, because you heard sometimes explosive elements. Okay, so how does the lithium-ion battery works? I think I have a film.
The lithium-ion battery, each battery is made. Let's take a closer look at one to see how.
Okay, so
a closer look at one to see how it works.
You can, in this film, it's a short explanation how the lithium battery works.
The electrical current reaches the cells via conductive surfaces. In this case, aluminum on one side and copper on the other. And just as in every other battery, there's a positive and negative electrode called the cathode and the anode. The cathode, or positive electrode, is made of a very pure lithium metal oxide. The more uniform its chemical composition, the better the performance and the longer the battery life is. As you'd expect, The anode or negative electrode is located on the other side. It's made of graphite, a form of carbon with a layered structure. The battery is filled with a transport medium, the electrolyte, so that the lithium ions carrying the battery's charge can flow freely. This electrolyte must be extremely pure and as free of water as possible in order to ensure efficient charging and discharging. To prevent a short circuit, there's a layer placed between the two electrodes, the separator. To the tiny lithium ions, the separator is actually permeable. The experts call this property microporosity. Let's take a look at what happens when a battery is charged. The positively charged lithium ions pass from the cathode through the separator into the layered graphite structure of the anode, where they're stored. Now the battery is charged. When the battery discharges, that is, when energy is removed from the cell, the lithium ions travel via the electrolyte from the anode through the separator back to the cathode. The motor converts the electrical...
Okay, so if you could see, the battery is made of two materials that can store the ions. Yes, the lithium ions. So in the process of charge, we move the lithium ions from cathode to anode. How they are built on the next slide, but generally in this solution is battery on accumulator solution. The most important thing is to move the lithium ion from one point to another by the separator. Of course, this is just the liquid separator, and the ions can go through this separator. So in the process of charging, they are moved to the anode, and in the process of discharging, the lithium ions move to the cathode. Okay, so generally, as you could see on the film, the porate graphite structure as an anode, of course, with the cuprum collector, and the cathode is a metal lithium molybdenum oxygen. I don't know what is the structure, but never mind. This is also the porite structure and the aluminum collector, and the electrons can move from the anode to the cathode. Yes, and we've got an electrolyte inside with, of course, this separation, and the lithium ions can move from the cathode to anode and from anode to cathode. Okay, so they are stored together. Cathode materials, as I said, is something, the combination of molybdenum, lithium, and oxygen. So maybe it's more important for chemicals reaction, but never mind. And the anode is the more or less the graphite. Yes, so it's carbon. And the ions can be stored in this porite system. Okay, so this is of course, they use the very complicated electrolytes inside because we want to have a long-lasting properties to store the ions in one side. So they must use a very complicated electrolyte inside. And this is the reaction, what happened inside the batteries. Okay, if someone wants to study it, so can study, because never mind. Okay, generally, when we build such a construction using lithium and carbon, we do have an accumulator which have the voltages about 3.6 or 3.7 volts per cell. Yes, this is the voltage on the cell, so it's higher than the cadmium or metal nickel batteries. 3 times it's higher. We have no memory effect. We have no lazy battery effect. So that was the problem of the current when we discharge the batteries, and we have 2 or 3 more energy density than the last examples. Okay, so we have much more energy in the liter of the volume of the battery. So it seems very nice, but there are also some disadvantages of the battery. They can leak. Yes, this is the problem, that there is a high, during this chemical process, there is a high pressure inside. So they can leak because a high pressure appeared inside. So they have some valves that causes that the pressure is going outside. But in this case, they can leak. They can explode. That was, and this is the, it was and it is a problem of such batteries, that they are very sensitive. I can show you a film. This is an example how the batteries, how lithium-ion batteries explode. We've got a typical, this is a typical battery. We charge it, I don't know what is the current, never mind. Okay, if you can see now that the higher pressure appears inside the batteries and the cover will blow. Yeah, you can see that it's something happened inside. Okay, we charge it. Oh, can you see that it's more and more pressure inside, so it seems to be blowing in the time. Oh, sorry. And if we overcharge the battery, it explodes. Okay, so it's not the best solution for the battery, because you heard about some problems in planes that the batteries explode, so they have the fire on the plane. So it's not it's not a very good solution, but we still use such a batteries, so because they store a lot of energy. But we have to be careful, because they can leak or they can explode. The problem also is that if we store these batteries in the magazine, of course, probably we can store them not highly charged or not highly discharged, because if we store them in the highly discharged, they can be broken. And if we store in highly charged, we can lose the properties of charging properties. Okay, so we generally store them in the half of charge for longer time, of course, because you can stop it for a moment. They can be charged and discharged. Okay, this is the typical charge, how we can discharge. This is the typical discharge process of the cell. If we can see, it generally doesn't depend on the current, so the resistivity of such a accumulator is very low, so we can use it for a high currents, because we have no losses on the battery ourselves. Okay, so it's almost flat from the beginning to the end of capacity. Yes, from the 5% of capacity, let's say it's 95% of capacity, up to 20. We've got the flat characteristic. So we've got this 3 point, it's better to say 7 or 6 here, 3.7, 3.6 Okay. That was the discharge process and how we charge this accumulator. It's not so easy comparing the nickel cadmium and the metal oxide batteries, because if you could see, we could damage the battery. So generally, the charging process is divided into two processes. Yes. First, we charge the battery with the constant current. So we've got the capacity of the battery, so we use the constant current. The current should be similar to the capacity of the accumulator. So if we've got 2000 milliampere hours, we can use 2 amperes to charge the accumulator, to charge the battery. Okay, so first we are charging with constant current, and we are checking what happened on the cell, what happened about the voltage of the cell. Yes? If we achieve the point of 4.2, more or less, of course, because it's dependent on construction. Every manufacturer said what is the proper point to change to stop the constant current charging. So if we achieve the voltage, for example, for this example, 4.2 volts, we are switching to constant voltage. Yes, this is the constant voltage charging. So we've got two processes: constant current and constant voltage. Yes. So we achieve this. We achieve the voltage, and wait until the current will, because this is the current, until the current will drop lower. Yes, it will be small, very small. Yes, this is the 0.1. Yeah. Generally, it is used that the 10% of the charging current, if we achieve 10% of the charging current, we stop the charging process. Yes, and in this case, we will have the 100 capacity of the accumulator. Okay, this is clear for you?
Yes.
Okay. So we've got two processes, charging and discharging. So generally, if we compare the batteries, we've got some advantages and disadvantages of the solution. Yes, of this three kind of accumulators. Okay. What's the problem of this kind of accumulator, of the lithium battery? The problem is that we cannot discharge it fully, so we can't go below a special value, because if we achieve for more of such an accumulator is 2.4 volts, if you are achieve this voltage, or the battery will have lower voltage, we can't discharge it again, because it's going to be explosive one, more explosive than it on the normal situation. So we have to use some elements that will prevent the discharge below the voltage, below 2.4 voltage. And if the battery cell is below this voltage, it prevents from charging. Yes. So generally we use the PCM circuits. This is typical. There are manufacturers that produce such an elements. That this is the cell. This is the pure cell. This is the battery. Yes, and this is the end of the package. Yes, because they are usually used with the packages. So we in this case we are checking if the voltage is okay. We can't, because we in the one. Okay. Okay. In one hand, we can't go below 2.4, and another hand, we can't go up to 4.2 volts. So this circuit prevents from the low and the high voltages, so over voltage and under voltage, and also sometimes prevent from current. So because some short current, because if we short the battery, on the circuits you saw that it's very low resistivity of the battery. So if we short it, yeah, the current will be very, very high and the battery can explode. So this circuit also protect from the high currents, okay, short current. Okay, so under voltage, over voltage, and over current. Okay, so this is the PCM circuit, which must be added to the battery because it's prevent from dangers. Okay, so there are of course different solutions for such a batteries. There are solution for our and to charge the elements like our cellular phones or something like this. There are of course batteries for automotive. There are batteries for manufacturers. There are different solutions and so on. So we can choose what we want. But generally, there are another type of battery. This is also lithium, but connected with the ferrum. This is lithium ferrum battery. I like them very much because it's new solution, and they produce the voltage 3 to 3.43 volts, so it's a bit lower. They of course have no memory effect, have no lazy battery effect, and a bit lower energy density than lithium-ion batteries, but they are better when we utilize them. So this is curves from the discharge process. But in this time, we have no such strong requirements for charging. So we can charge it any type we want, just to find out if we got as voltages on the batteries, and do not need the PCM system because they can. It is not necessary to use this system. Okay, what next? Okay, can we make a 5 minutes break? Hello, can you hear me? Can you hear me?
Yeah.
Okay, can we make 5 minutes break? Okay, thanks so very much. I'm back. Can we start again?
Yes, we can.
Okay. So what are the properties to store the energy? We're talking on our first or the second lecture, we're talking about capacitor, and that was the device that we can store the energy. We can store the energy just using two plates with small distances, but of course the density of the energy we could store on the plates wasn't too big. So as we could see that we can use some chemistry, some electric processes, not electromagnetic, electrochemical processes to store the energy with higher density. So in the last years, it was a how to say, we are going towards to join to many things. So they thought, what happened if we join the capacitor with the electrolyte accumulator? And this caused that a supercapacitor appeared on the market. The supercondensator joined, as I said, two properties. One, the property of the capacitor, so we can discharge it any current we want, and we can charge it anytime we want because we do not lose any material and we do not use an electrolyte inside. And if we join it with the accumulator with typical chemistry, we can have something, a hybrid of two elements. So this is the supercapacitor. So in generally, the ability to store using such elements are very, very high nowadays, and they are going to be used more commonly in our devices to store more or less energy inside. Okay, so generally it is yes, this is two elements. We've got this two layer and the electrolyte inside. So in the matter of fact, we've got ability as a yes, we've got the capacitor, typical capacitor. We've got two layers separated and electrolyte between the layers. So, but we still have the capacitor and the electrolyte battery, the electrolyte capacitor, the electrolyte accumulator between them, or parallelly, or something like this. Yes, this is the capacitor connected with the accumulator with the chemistry. Yeah, so we've got the fusion of two physical properties, the typical capacitor and the accumulator. So this is, of course, how it is built inside. We've got negative and positive electrode because in this is not electrolytical capacitor, but something like battery. So we have the polarization of this element. So do remember that supercapacitor have the polarization. Okay, so we've got the this is the Helmholtz plane. The Helmholtz plane, it is the plane, it is the layer when the process of changing the electrons appeared. Yes, from the electrolyte to the collector. Yes, because we've got the typical capacitor, yes, with these two layers and the electrolyte inside, and the ions from the electrolyte goes to the inner Helmholtz plane, and in this process we have the ions going to the plane. So as in battery, as in accumulator. So in generally, we have such a situation that when we discharge the supercapacitor, we can, this is the voltage on the capacitor. So we discharge it for a moment and the voltage drops to the zero as in the typical capacitor. But if we stop the discharging, the ions from the electrolyte goes back to the plates of the capacitor, and we can, so we've got the energy in this plate, and we can use it. So we can use the current, and again. So if you can see, maybe it's not the best chart, but generally in this situation, we can, maybe it should be like here, because, but this can explain. So we've got the power, we've got the electricity going from the capacitor, yes, and we can discharge them, and then the electrolyte charge the capacitor, and we can discharge it again. Of course, if we discharge this element slower with lower capacity, we've got this process like batteries. Okay. So this is the supercapacitor. Okay. So generally, if we compare the ability to store the energy in the different kind of accumulators, here we've got the liquid acids, lead acids used in our cars, but they need some services, they are very heavy and so on. Here we've got our nickel cadmium, nickel zinc accumulators. Here we've got alkaline batteries, yes. Nickel metal elements, yes, and our lithium ion. Yes, this is lithium metals or lithium ferrum or lithium ions batteries. So this is where we are. Of course, we've got the supercapacitors, but they should be like here because they do not store a lot of energy, but we can store it as many times as we want. Okay, so this is where the supercapacitors are. So they are between typical capacitors, the typical electrolyte capacitors, and the batteries. Okay, so this was yes, this is what we have to store the energy, and if you want to charge and discharge the elements. Is it the future of our system? I don't know. Nowadays, lithium ion is going to be a good solution, but I don't know it's good for our environment because the lithium is very expensive and it's very not good for our health. So in 10-15 years, we will have the problem of the batteries, lithium batteries. So, but electricity will come. So this were the examples how the electrical batteries, electrical accumulators works. But we have another solutions to store the energy. We've got something called fuel cell. What is the fuel cell? I've got a film for you. Okay, fuel cell is connected with storage of energy in gas. We use the hydrogen. This is the gas which we can use to store the energy, because hydrogen has two electrons inside. So we can say that we have these electrons, and if we divide this gas, this helium, to the somehow we extract these two electrons from the atoms, we'll have this extra electrons for our electricity. Okay, so it's not a burning process like in petrol, but this is the process that we can have the electrons from the hydrogen. Okay, maybe this is the future of our environment. So on the anode, at the anode, this is a catalytic process, and in this catalytic process, we separate these atoms from the hydrogen, yes, from protons and electrons. Okay, so that was how we can extract the energy, extract the electrons from the helium, from the gases. Okay, so when we are using such a construction with, of course, special plates, special elements that can extract the electrons from the atoms, we can have the fuel cell that is very pure, because we've got hydrogen as an input. From the air, we've got and then we've got just a water at the end of the process. So this is very nice process. Okay, so the problem, of course, is how to store the gases, because generally gases are very well stored, but hydrogen is very small, and we can't store it very well. But maybe in future someone will solve this, will solve the problem. So this is the equation. This is the chemistry of the process, but it's just if hydrogen, which is distracted to the electrons, goes to the water. Okay, because on the anode and on the cathode, we've got oxygen and electrons, and it goes to the ions. Okay, so in this case, we can have ability to store the energy. Okay, of course, we can't reverse the process in the fuel cell, but we can produce hydrogen in other processes. Okay, so that were the solution to store the energy. Of course, we have some European standard for batteries generally. Yeah, so we've got a lot of parts, how to store the energy, how to store the batteries, how the watch batteries should be made, how safe, about the safety of the lithium batteries, and so on. So we've got a lot of European standard, and every manufacturer should know that the standards are very complicated, so they should know about the standards. Okay. Okay, so that were the elements that store the energy. But if we could see that for all of these elements, the voltage on the end of the elements is not stable. So it changes due to the time, due to the current, due to the temperature, and so on. But for our devices, we generally need to have a stabilized output. Yes, because if we use processors, if we use some amplifiers and so on, we should have stabilized output. So we've got unstabilized input voltage from the sources like supercapacitors, like accumulators, like fuel cells, and so on. So we have to do something to stabilize the output voltage. Of course, we need to make some control elements which will stabilize the voltage up to reference voltage, because the reference voltage is the voltage we should set for our devices. Yes, if we use processors, it's typically 3.3 volts or 1.8 volts, and so on. So we are generally need to use some stabilizer. The simplest solution is to use a Zener diode. If you remember, the Zener diode has the reverse current in the Zener voltage, so we can set the voltage by it is set by the manufacturer, and using two resistors we can achieve we can stabilize the voltage on the end of our circuit. But the problem of this circuit is that we need to have more current going through the Zener diode than it should be similar than by our circuits, our load. So it is not the best solution because we lose energy. Okay, so the solution is to use transistor, and in this case we will have the better solution, because using smaller current going through the diode, we'll have higher current going through our load. Okay, so this is a simple solution. This is simple analog, of course, solution that we utilize to stabilize the voltage on the reference voltage. Yes, this is if we use a Zener diode 5.6 volt, we have voltage drop here, because we know it's like a diode here, 0.7, so we will have more or less 5 volt as a stabilization voltage with higher current, because it goes through the transistor. Okay, of course nowadays we do not use just one transistor and so on, because it's not linear, it's not stable, it loses some voltages, so it's generally not utilized very commonly. But if we have no idea, so we can use them. Generally we use some complex regulator circuits. Yes, and this is a solution of the series of the regulator. You probably know this circuit, and we just add the non-stabilized input, and we have stabilized output. In this solution, we've got 0.5 volt. Yes, this is 0.5 volt as an output. We could have 12 or something, 0.9, 0.25. It changes them. Just these two numbers, and this means Yes, this is corresponding to the stabilization, the output voltage. Okay, so this is a solution for stabilization the voltage, but in this case we can use one stabilizer for one voltage. Yes, so we must to buy a special circuit with special name to have the voltage we needed. But we can use also voltage regulators that in where we can set the output voltage using outside elements. So the LM317 is an example of such a regulator. In this case, we can stabilize the output voltage by setting the proportion of these two elements. Okay, so if we've got the variable resistor, we can have variable output stabilization process. Okay, this is how we can calculate the output voltage using two resistors. Okay, so if you can see, we can use some simple elements like transistors, but more complicated inside, to stabilize the output voltage from the different voltages on the input. Of course, the input voltage must be higher than output voltage, because in these elements have no ability to increase the voltage. Okay, so the last slide probably is that nowadays we are trying to have the energy from everything from our environment. So it is called something like energy harvesting. So we try to harvest the energy from, for example, human activities from our environment. So if we are walking, we are shaking our body, shaking our hands, we are moving our hands. So in this case, we are making work in a matter of fact. So maybe there are some abilities to harvest this energy, and there are some, for example, vibration generators. So if we are vibrating vibrations, so we can harvest energy from this vibration. Okay, or we can harvest the energy from the outside light, like electrovoltaic cells. We can harvest energy from difference of temperature, for example. Maybe we can connect one part to our body which we have higher temperature than outside world. So the difference of the temperature can produce the electricity. We can harvest energy from radio waves, because radio waves are everywhere, so we can have some elements that can transfer the radio waves into the power which is needed for our devices. Okay, so that's all for today. The future is yours, so we will find probably some more elements that can harvest the energy, that can store the energy more safely and more efficiently. Okay, thank you very much for today. Do you have any question? If no, thank you very much, and we will see next time. I will be talking about power management and some suppliers, how we build some suppliers, how we are able to have the more voltages from the smaller voltages and so on. Okay. Goodbye.
Goodbye.
Thank you.